displacement at B. So we need to find the displacement at point number B here, right? So we have equations delta is equal to small n capital N L over E A, right? So that is the axial stiffness, and that is a very simple equation. That is only one equations that we come across with the virtual work method. That is not plenty of equations. There are two equations, by the way, one for truss and one for beam. When the beam questions comes, I will introduce to you. Now we need to find this displacement. How many members you have here? You have member 1, member 2, member 3, member 4, and member 5, as you can see here, right? So you can just number them. There is no rules. You can number them as you need it. So in that case, we have N1, N1, L1, E1, A1 plus N2, N2, L2, E2, A2, and tick tick tick. You got a message N4, N5, N5, L5 over E5, A5, right? I just convert the small equations into the long equations by saying how many members I have in the truss. Right? Simple, right? There is no any issue. So we have very simple equations, small n, capital N, L over EA. Depending on number of members, you can extend that equations into the long equations. Now, there are two things that we are working on. One is a virtual systems. Sorry, let's do the, what is this N? N is the internal axial force in virtual system. This capital N is internal axial force in real system, and this L is the length of the members, like you have 4 meters and 4 meters and so on. And E is a Young modulus given to you in the assignments everywhere. The Young modulus is known depending on the materials and area, cross sections area of the members where the members is made of. You can see as well, right? Okay, so let's say we want to calculate each parameters one by one. Let's say we want to do the real system first. Real systems, in the real systems we're going to get N1, N2, N3, N4, and N5. Okay, 5 axial forces that we're going to get in the real system. So let me draw the real system first. Roller and pin, and we have 50 kilonewtons. And we will get A, B, C, and D, and we go down. Over here we have 100 kilonewtons. This is 4 meters, 4 meters, and 4 meters here. So that would be square root 32, I think. Square root 32. Right? I just draw the truss again in the given in the questions. Now let's draw the free body diagrams by removing the supports. That okay, there is a reaction force RA. Let's say there is a reaction force RC, and there is a reaction force, let's say horizontal reaction force HC. Let's say sum of the moment at A equal to 0, anti-clockwise is positive, minus 50 kilonewtons times by 4 meters plus RC times 8 meters minus 100 kilonewtons times by 4 meters equal to 0. Right? You done plenty examples by so far now that how to calculate the reaction forces in truss and beam. So I just got it. So minus 200 kilonewton meters minus 400 kilonewton meters plus RC times 8 meters equal to 0. So RC equal to 800 kilonewton meters over 8 meters equal to 100 kilonewtons. Does it looks right? Oh, 600 says what I mean. There is something does not look right. So 600 divided by 8, 75. That sounds a little bit better. You can stop me if you have any questions or if it's going too fast. So far so good. Okay, sum of the force in the y direction upward is positive. So reaction force going up A, reaction force C going up minus 100 kilonewton equal to 0. We substitute RC equal to 75 minus 100 kilonewtons. So RA equal to 25 kilonewtons. So we have RA, RC, sum of the force in the x direction equal to 0 minus HC plus 50 kilonewton. So HC equal to 50 kilonewtons. So we found all the reaction forces. Right. So we found all the reaction forces. Let's find all the okay. We're gonna keep the numbering same 1, 2, 3, 4, 5. So let's redraw this one. 1, 2. This numbering is what can I say? It's not. It's just the users can define that easily. There is no any rules that someone need to put that numbering. There is no any rules. That's what I mean. A, B, C, and D. 100 kilonewton here. Reaction force here. 50 kilonewtons here. Reaction force 25 kilonewton here. 75 kilonewton here. And 75 kilonewtons here. Right? And this is 4 meter. 4 meter. 4 meter. Square root 32. Square root 32. Yes, please.
J is meant to be 50.
Oh yes, thank you. Thank you for that. Yep. All right. So now we use joint methods to find those internal axial forces. Let's take the joint number A. There is no any rules as again. We can take any joints, but let's start from left side. Let's draw joint number A. We have these forces. This is 25 kilonewtons. Let's put this is N1. Let's put this is N5 and 4 square root 32. You know these styles, right? I think you done the big examples in the assignments. So by this time you absorb all these joint methods by heart. And probably if you make a mistakes in the middle somewhere and you screw up and you go back again and do it all again. So that's the part of exercise. So it is better that we done some examples by yourself, so you have some understanding now. So I think we can quickly run through this one. Sum of the force in the y direction upward is positive. N5 times 4 on square root 32 plus 25 kilonewtons equal to 0. N5 equal to minus 25 kilonewton times square root 32 on 4. So you got minus 35.36 kilonewtons. Let's make a list somewhere. Let's make it N1, N2, N3, N4, and N5. We got N5 minus 35.36 kilonewtons, negative sign meaning compressions. I think the virtual work method is very simple. It's just having two cross examples in one example, and there is a one simple equation at the end to find the displacements. Okay, so that's N5 done. Let's do the N1. Sum of the force in the x direction equal to 0. Left to right is positive. N1 is positive plus N5 times 4 on square root 32 equal to 0. Let's substitute the N5 value. which is this negative 25 times square root 32 on 4 times 4 on square root 32 equal to 0. This cancels. So N1 equal to 25 kilonewton tension positive. All right. Any questions so far? Yes. All good. All right. We continue the journey. Okay. Joint B looks simple. Yes, please. Don't worry. Okay. All right. So here you go. Joint B, 100 kilonewton coming down. This one is what? N1 and N1 25 kilonewtons we got. By the way, this is N1. This one is N3 and N2. This one is N3, N2. By looking at the figures, sum of the force in the x direction N2 is 25 kilonewton tensions, N3 is 100 kilonewton tensions. So let's put this one in. 25 kilonewton tension, N3 100 kilonewton tensions. All right, so far so good. N4, we need to pick the joints. I think joint DC looks good. That can help us to get the N4. So let's draw up the joint C. I think this is 75 kilonewtons. Let me check. 75. This is 50 kilonewtons. This is N2, I think. And that N2 would be 25 kilonewtons. And this is N4, 4 square root 32. Let's say sum of the force in the y direction upward is positive. M4 times 4 on square root 32 plus 75 kilonewtons equal to 0. So N4 equal to minus 75 kilonewton times square root 32 on 4. You got minus 106.07 kilonewton compression. N4 minus 106.67 compression. Right? Yes, please.
Compression, we make it negative.
Sorry.
So when you go back, when you were writing.
When you are writing, yes, all the list.
So compression you write is negative.
Yes. And as you know, there is no rules. Someone will not gonna force you to say that tension is always positive. But when you start your examples, we make these assumptions. There are a couple of assumptions we make. Sorry. What is the assumptions? Assumption saying that tension positive, compression negative. Oops, sorry. Compression negative, up force positive, down force negative, anti-clockwise moment positive. These are my list of assumptions, and I stick with that assumptions throughout my examples. No one forcing you to make these assumptions. You can take a tension negative, compression negative, but you stick with that one throughout your example to make it consistent. And you will get the same answer. at the end displacements. Okay. So those are the some assumptions. We make it at the start and we stick with that assumptions. Some software like SpaceCase, they take it tension negative. Right. So when you're comparing your assignment questions answers with your calculations, you might need to switch it. Okay. And in the comments, therefore, we have a comment and suggestions about this one. I want to see your understanding that, oh, that is not matching. Why is not matching? That's your part to say that therefore this one is not matching. Okay. So that's all good. And we cover everything. We are not asked you to have your own research. We talk about all those things in lectures and workshops, right? And of course, you can ask me questions still if it's something missing that is puzzling you in your assignments. All right, so that's all done. Real system done. Virtual systems. And if you look, there are a lot of vocabulary which I don't feel right now good that I'm putting those things. But if you watch the lectures, if you attend the lectures, I think we have a strong 2 hours discussion. I think many students don't. I'm not sure. Many students not attending the lectures. Yesterday I start my lectures. I'm not forcing anyone to start lecture, but I'm not sure how you're going to absorb all the information if you don't attend the lectures. But that's okay. Yeah, but I don't feel so much good right now that I'm putting all this new wording in the workshop straight away. But anyway, because I can't go back all these 2 hours again, otherwise we will not finish this example. So we're going to run the virtual systems. Now, what we do virtual systems? We have these examples here. Let me. So in the virtual system, there are 2 systems, real system and virtual system. So in the virtual system, we redraw this all the same geometry except the loading. So let's redraw it. So this is my truss. All the supports are there, roller supports, pin supports. We have a B, I think we put C here before, so let's keep it consistent with our previous figures. We have a number 1, number 2, number 3. I think this is number 4 and this is number 5. We just keep it consistent with our real system and virtual system. We don't want to change it. Now, what is the difference between real system and virtual system? We're going to put the virtual load. We're going to put the virtual load, very important, where you want to find the displacements. You want to find the displacement at point B, then you find the virtual load at the point B in the directions where you want to find the virtual load. If you want to find the vertical displacement at point B, you put the virtual load in the directions where you want to find. If the question is asking you to find the horizontal displacement at point B, you put the horizontal virtual load at point B. Okay, is it clear? So this one, and again there is no rules. This one that I put, there is no unit for that one. This is just a virtual. There is a dummy load. There is no load. This is just to trick the systems, right? So therefore we put the one, no unit, 1 unit load. So when we get the answers, we don't need to double or something like that. So if you put 10 here, then your displacement would be double by 10. You need to divide by that. So keep in mind that again there is no rules that why I put 1. You can put 2. You can put, this is dummy load as I mentioned, but your displacement would be double if you put 2 here. Okay, the final display. So to make a mathematics simple, we keep it 1. All right, and we repeat the whole procedures again, and we find small n1, small n2, small n3, small n4, and small n5. These are all internal axial forces in the virtual system. So let's do it again. All the real loads are gone. As you can see, I read out of figures. Put the supports, geometries are there, and we put the virtual loads only. So let's put the reaction force again. Reaction force at A. Reaction force at C has C. Okay, let's say sum of the moment at point A equal to 0. So we repeat the whole procedure again, right? That's we done in the real system. So RC times 8 meters, because this is 4 meters, 4 meters, and 4 meters, minus 1 times 4 meters, and that's it. So RC equal to 4/8, which is 0.5 kilonewtons. And sum of the force in the y direction upward is positive. RA plus RC equal to 0. RA plus 0.5 equal to 0. Yes. So all this one minus 1 equal to 0 and minus 1 equal to 0. RA equal to 0.5. Okay. So we have a, by looking at the figures, it looks like a symmetric. So we just need to do the half. That's a good thing. You remember that is we done one example which is symmetric. Symmetric meaning you have to do the half one. 0.5 going up here. 0.5 is going up here. This is 0. There is no reaction here, 0. So if it's 5 and 4 would be same. Do you agree with me? And 5 and N4 would be same. And N1 and N2 would be same, right? Because we have symmetry. You can see line in left side and right side both are equal. So half work is done. So let's do the joint number A. Small n1, small n5, 0.5, joint number A, 4 square root 32. So sum of the force in the y direction upward is positive. N5 times 4 on square root 32 plus 0.5 equal to 0. N5 equal to minus 0.5 times square root 32 on 4. Give you minus 0.71 N5. And that is compressions. N5 minus 0.71 compression. And that N5 would be same as N4. So let me put it that way. All right. If you want to do the calculation, you can do the joint C and you will see the matching. All right. Joint A. Then we can find some of the force in the x directions. Left to right is positive. N1 plus N5 times 4 on square root 32 equal to 0. N1. N5 is minus 0.5 times square root 32 on 4 times by 4 on square root 32 equal to 0. So N1 equal to 0.5 tension. N1 equal to 0.5 tensions and N1 would be same with N2. And N3 joint B is simple. One N2 N1 N3 N3 would be 1 tension. N3 would be 1 tension. All right, we have all the recipe now to use the virtual displacement equations, which is small v capital N1 L1 E1 A1 A1 plus N2 N2 L2 E2 A2 plus N3 N3 L3 E3 A3 N4 4 L4 E4 A4 N5 N5 L5 E5 A5. Understand this one? I just have an expansion of these equations. We have 5 members. If you have 10 members, you do 10 sums. If you have 15 members, you do 15 sums. If you have 2 members, you do 2 sums. All right, we have all the values. N1 small. Do you remember we list them, right? N1.5. N1.5 Capital N1, 25. L1, 4. EA is a constant, we have not given. If it is given, make sure your unit are consistent. I think you are practicing those units in the assignments. We intentionally give you in the different units, so you can tweak those units carefully, right? So I think you have some exercise now how to use correct units. But of course, I will show you again here. N2, 0.5. Capital N2, 25. 4 meter over EA. Capital N3. If you get a different E and A value for each members in some of the assignments, you can find that E and A values are different. So then you need to put the different EA values. OK. Here it's same. So therefore I keep it consistent. Now small N3 is 1. Capital N3, 100. 1 times 100. And the third member is 4 again, EA, plus N4 minus 0.71, capital N4 minus 106.67, and this is 32 over EA plus N5 minus 0.71, capital N5 minus 35.36 times square root 32 on EA, right? So 0.5 times 25 times 4, you got 50 over EA. 50 over EA. 400 over EA. 428.43 EA. $142.02 EA. All right. Does it make sense? Any questions? Anything that does not make sense? Any parameters that you think that is coming from the sky and it's not making sense? We can go back and check it. Yes, please. Why B is down? Well, you can check from the point B. Vertical displacement at B. If you have 100 kilonewtons, there is no any other loads in the system. What do you think that will go? So therefore it's down. All right, so let me show you Excel as well. I don't want you to just feel that it's all hand calculations. All the engineers generally use the Excels. Yesterday in the lectures as well, we have used the Excels. So in the assignments, when you want to do the big calculations, I'm not sure how many members you get, but there are plenty of members. There are 8, 9 members, so you will get many members. You can use the Excels to let's put the members. Let's say we put member AB, member BD, member AC. Or let's put the 1, 2, 3, which match with our 1, 2, 3, member 4 and member 5, right? Yes, please.
Question you get. Could question 5 got that many? Question 4 got that many?
Well, I did not choose intentionally, but by luck. No, we need to have some variations, otherwise. Well, in some cases they will get harder, some are lower, but they are randoms. So it's not someone I pick it intensely. All right, so let's do the Excels. Okay, just put this in members. So we calculate capital N first, I believe. So let's put the capital N first. Let's put the capital N first, and N1. Let's copy this N1 here. 25, 2500. So 25, 2500, and then you have minus 106.67, minus 106.67, minus 3536. Are you following this one, right? Is all good now? Okay, you can stop me if you don't understand any of this. Let me get this copy. Let me put this one here. So we have it in the systems. Now we have small n, and the small n is, yeah, you read for me. 0.5, 0.5, 1, 0.71, and the same. Okay, that looks good. Then L, L1, L2, L3, 4, 4, 4. Is it better? Then we will have E, and we will have A. We don't give on E and A, but we will assume some value. Let's say we have 20,000 megapascals, Newton per millimeter square. Let's put this value here. Okay, let's put the area 100 by 100. Let's say you have a cross section area. Where is my pen? Let's put this cross section here. Let's assume that cross section area 100 millimeter by 100 millimeter. That's the made of these truss members. So let's say 100 by 100. That makes it millimeter square. And let's drag it down. So far so good. And in the final columns, let's say N, capital N, L over EA. So this times this divided by E times this G3. I think this is really not going to work.
You need to put brackets sorry. Between C and E.
No, don't require. It's not needed. Yeah, year 9. But yeah, it will not gonna make a difference. I know. Okay. We done a lot of coding, so in coding we use this. It's not required because you multiply. You know this multiplication bracket. You do bracket first, then you do multiplication and division. That is a rules. That is a short name as well. Yeah, something like that. There is a rule. So probably in year 8, year 9 schools we belong that. So but for you, I put the brackets. All right, but it's not required. All right, so it does not looks good over there because there are units are everywhere. So this is in kilonewtons. This is no unit. This is in the millimeter. This is in millimeters. So let me make it in the same unit. 4 times 1000. So that is your millimeter. And let's multiply by 1000. That is in millimeters. Let's multiply this one into newtons. and let's multiply this one in the newtons. Let's put this one in the Newton. Let's put this one in millimeter. This Young modulus megapascals, meaning Newton per millimeter square. And this area is in millimeter square, right? So everything looks good. Equal to times by 1000. So text looks good, and then we're just going to sum it up. And that is in millimeter. Right? Student asked me the questions. Can I do this one in the assignments and just put the screenshot? Well, first do the hand calculations and then do this one and put the screenshot. But straight away do this one will give you a hard time in the exam. So you need to have a unit and all. This is just an extra things for you to compare because you have a lot of hand calculations. So therefore, okay, everyone understand that? Someone might say it's not matching the answers. We might need to do some work here. So this is in kilonewtons. So the Young modulus is 20,000 megapascals. So 20,000 times 10 raised to power 6 pascals, which is 20,000 times 10 to the power 6 Newton per meter square. We need in kilonewtons, so 20,000 times 10 to the power 3 kilonewton per meter square. Right? Area equal to 100 times 100 millimeter square, which makes you 10,000 millimeter square, and that's we're going to divide it by 1000, divide by thousands to get it in the meter square. 0.01 meter square. So let's see if it is coming up or not. Yep, 5.35 times 10 raised to power 3 meter. So 5.35 millimeters. Is matching? 5.35, and that is match. Right, any questions? If any units, this is very important on the right side one. It's exactly the same thing that you're doing in the assignments right now. Millimeter, meter square, and so on. We are recording in case if you want to go back and check these calculations. Any questions? If you have a trust problem given to you in the virtual work systems, you do real systems, find N1, N2, N3, N4, N5, N5, N6, depending on how many members you got. You put the virtual load at the point where you want to find the displacement in the directions where you want, in the direction the displacement that you want to find, and remove all the real load and find N1, N2, N3, N4, and so on. And there is a very simple equations that you can use. Make sure that your Young modulus and area is same for the each members. If it is not same, you need to use different, because some examples in the assignments you might find different area, different Young modulus. Then in that case you have E1, A1, use different E1, A1 value. All right, space gas. It will not gonna open here. Anyway, but you know the space gas story, right? If I can make it work beforehand, let me load it for Software Center and see if it is still gonna pick it up. Give me a minute, maybe at the end I will show it to you if it is loaded from the Software Center. I think this is required. I think that's okay. I think you know the space gas things. Okay. All right. Now let's do another examples. All right, so we need to find a displacement at point B. It does not say in the examples, but you can add here. Determine displacement at B here, right? P could be any value, 10 kilonewton, 5 kilonewton, 20 kilonewtons. It's just a variable there, and length could be any length. Okay, so first thing first, rules is same: real system, virtual system, and one simple equations. The one simple equations that we have, delta is equal to small m capital M over EI, right? And you can see there are two segments. So in that case, is small m1 capital M1 over E1 A1 plus M2 capital M2 E2 I2, right? Because you can see there are two segments that we are working on. So in that case, we have two different segments value. Now let's do the real system first, because this is real, this is virtual. As you know, the small letters that we use for virtual, big letters we use for real. So let's do the real system first. Real systems. So let's draw the real systems. P, A, B, L by 2, L by 2, total length is L, and so on. Okay, so let's do this x1 measuring from here, x2 measuring from here. So we need to find the reaction force, by the way. So the reaction force that we're going to get, AX, AY, MA. There are three reaction forces. AX equal to 0, there is no horizontal force. Sum of the moment at A equal to 0, anti-clockwise is positive, minus P L by 2 minus P times L plus MA equal to 0. So MA equal to PL plus PL divided by 2. All right, and sum of the force in the y direction upward is positive. AY going up, minus P equal to 0. So AY equal to 2P. Right, so if I redraw this beam, 2P, P, point A, point B, L by 2, moment, PL plus PL divided by 2. And the X1 coming from here, let's break the beam. P distance x1, capital M1, PL plus PL divided by 2. Right, so sum of the moment at cut equal to 0, anti-clockwise is positive, M1 plus PL divided by 2 minus 2px1 equal to 0. So capital M1 equal to minus PL divided by 2 plus 2px1. So M1 equal to minus 3PL divided by 2 plus 2px1. Alright, capital M1 done. We've done this kind of example plenty times. You know, drawing the bending moment diagram, shear force diagram, make a cuts and find these M equations. Even in the week number 5 in the elastic curve equations, we done that one. So therefore I go fast here, and then you make a cut, another cut here at a distance of x2. So here we got, P distance x2 and M2. So sum of the moment at cut equal to 0. Anti-clockwise, we just make this one square because we need that equations. So would be minus px2 minus m2 equal to 0. So m2 equal to minus px2. We might need these equations. That is a real system, by the way. Did I write real systems? Okay, let me put one real systems. And then virtual systems, number 2. Let me put the questions back. So we need to find the displacement at the point B, and that would be vertical displacement. So in the virtual system, we draw the virtual systems, we put the load at the point where you want to find the displacements, right? We are finding the displacement at the point. Sorry, we finding the displacement. Okay, don't worry. We are finding the displacement at here. Let's say point C. Okay. So in that case, we have a virtual load 1 at the point where you want to find a displacement. Just make a correction there, A, B, and we need to find the displacement at point C. Okay, so we put the virtual load where you want to find the displacements. We just want to find a displacement at point C. Okay, if they ask you to find a displacement at point B, don't worry, you just put the 1 at point B. Okay, that is no anything, and I put down because that would be downward displacement. So in the directions, if you put upwards, what happens? Your answer would be negative. There's no any issue. If you ask me questions why up or why down, how do I know? Sometimes I can't imagine multiple loading. So no worries. If you don't know, just put the loading, the virtual loading, the way you like it. And if your answer is negative, meaning that this direction that you assume in the virtual load is not correct. Okay, but at the moment I can see by these conventional loading conditions, P is all going down, the beam will have a deflection downward, so I put this downward. So that's okay. We will follow the same conventions. We find the reaction force is first. Reaction RA, horizontal reaction is 0. Reaction MA, A, point C, point B. We have 1 here, no units. And then we will say that sum of the moment at A equal to 0 anti-clockwise is positive, minus 1 times L by 2, and plus MA equal to 0, MA is equal to L by 2. RA going up, 1 is coming down, so RA equal to 1. So if I redraw this one again, this is 1, this is point C, this is point A, point B, L by 2, 1 here, moment, L by 2. Right. So the x1 and x2 that we have taken in the real systems, we keep it same. We don't change it in the real system. Otherwise, we will have a problem. So we keep it exactly the same where it started, where from left to right, where the same exactly the point. You can see here that we have x1 started from point A and here, and we make the exact same cuts. All those cuts are matching with the real system and virtual system. Don't make those smart decision to have x1 at the different locations and this one. It will just causing errors in the calculations. So as you know, we are not that smart enough to have to challenge. So I would just make a same cut as a real systems. Right. So when I take this first one, which is 1, this is by the way point A, we make a cut small m1 at a distance of x1, reaction moment L by 2. So sum of the moment at cut equal to 0, anti-clockwise is positive, small m1 plus L by 2 minus 1 times x1 equal to 0, m1 is equal to minus L by 2 plus x1. This will gonna take it. We need this. I put the square because we might need this in our later equations. And we can make another cut, point B, and cut small m2 at a distance of x2. There is no loading, so m2 would be 0. All right, finding those m1, capital M2 is exactly the same that we're doing in last 5-6 weeks. That's nothing new, right? And capital M1. Therefore, we have taken first 4 weeks to revise you all those things, right? Because if I take this straight, M1, M2 would be real challenging. So we done this finding those internal moments, the equations. So now very simple equations, delta C equal to small m1, capital M1, E1 A1, EI I1 plus M2 capital M2 over E2 I2, and I think there is an integrations. Someone might say, why do you do integrations? I can explain you that. 0 to L by 2, 0 to L by 2, dx1, dx2. Now I will explain you those each terminology one by one. I don't want to skip anything and where those are coming from. Now the first segments that you have taken is the x1, and you can see the x1 is changing from 0. Do you remember this is the x1? So it start from 0 and finish it here, L by 2. Do you agree with me? This x1 will not going to cross the point C. Right? They will just gonna start at 0, finish at L by 2. So you agree with me that 0 to L by 2 limit for this x1. Right? 0 to L by 2. If you are, as I mentioned, if you are using different conventions, then your M1 would have a different one, your capital M1 has a different convention. Therefore, I told you to consistence between small n1 and capital M1. So then you have one integration limits. Okay. So these 0 and L by 2 is coming from x1. That is nothing new. X1 is start from 0, finish at L by 2. Similarly here, x2. If you come back here, that we started x2 here. So that is the 0 and finish it at this point, 0 to L by 2. If someone started x2 here, then you might have L by 2 to L. Right? That's limit. So depending on where you started, you need to have these limits, right? So you know M2 is 0, so that makes our life easy. So we end up with only one, M1 capital M1 E1 I1 dx1, right? If you have M2 not 0, then you need to have this extra quantity carry over throughout the calculations. But you can see in here M2 is 0. So we straight away put M2 equal to 0, M1 multi M2, capital M2 multiplied by M2, that is makes 0. So let's plug the value. EI is constant, so let's get them out. 0 L by 2, small m1, capital M1 dx1. 1 over EI. Let's plug the value. Small m1 minus L by 2 plus x1. Capital M1 minus 3PL divided by 2 plus 2px1, and that is dx1. Understand? I just plug the value of small m1 and capital M1. All right, 1 over EI, 0 to L by 2. Let's expand the brackets. 3PL square on 4 minus 2px1 times L by 2 minus 3pl 2x1 minus 2p x1 square. We can take the p out. 3l square on 4. This cancels. x1l 3l by 2x1 minus 2x1 square. These are the like terms. 3l square on 4. So 2 this would be minus, right? So minus 5 lx1 over 2 minus 2x1 square dx1. And this is plus. And you can just 3 square on 4 x1 5l divided by 2 x1 square on 2 2 x1 cubed on 3 0 to L by 2 3l square on 4 times L by 2 5l divided by 2 half L square on 4 2 on 3 L cubed on 8, right? It's just the integrations. 3L cubed on 8 minus 5L cubed on 16 minus 2L cubed on 24 all good? Good, okay. All right, sorry if it is quite long. 6. I think something I mixed up. Oh, this is always plus. You don't need to do it this kind of heavy in the side. Yes, please. Huh? Yeah. How about now?
Yep.
Yep. Last bit. Last one. All right, let's finish this last one, and then if you have any questions about the assignments and all, I'm happy to help. All right, so determining the slope at C, there is a point C here that we need to find the slope. Now, when you put the slopes, you can't put the virtual load. You need to put the virtual moment. Okay, so that's the change here. So you need to put the virtual moment there. Equations is same. Real system, virtual systems, and then we follow the same trend. All right, so first thing first, we're going to find the reaction. First thing first, we will have a real system. Real systems, you have pin at A, roller at B, point C, and that is 2250 Newton per meter. Just check the unit, 1500 newtons, 2.4 meters, 1.2 meters. Okay. Right, and we need to find the slope theta C using the virtual work method. So first thing first, let's draw the AY, BY, 2.4 meters, 2250 Newton per meters, 1500 newtons, 1.2 meters, C, B, and A. So sum of the moment at A equal to 0, anti-clockwise is positive. BY times 2.4 meters minus 2250 Newton per meters times by 1.2 meters times by 1.2 meters over 2, so 0.6 and 3 meters minus 1500 newtons times by 3.6 meters equal to 0. Right, so BY equal to 5625 Newton. Sum of the force in the y direction upward is positive. AY going up, BY going up, 2250 Newton per meter times by 1.2 meter coming down, minus 1500 Newton coming down. We substitute By 5625 Newton. So Ay equal to minus 1425 newtons. I think finding the reaction force in the real systems. We're gonna follow the same trend that we done it in the last examples, x1 and x2. X1 start from left, x2 start from the right. So let's draw up again. Ay is coming down, let's say 1425 newtons. A, By going up 5625 newtons. Point B 2.4 meters. And that would be 2250 Newton per meter and 1500 newtons, 1.2 meters. And let's make two cuts. First cut at a distance x1 starting from point B. Second cut that x2 and that start from point number C. Okay, and we keep it consistent for both real system and virtual system. We're not going to change it. No rules. You can start x1 from this side or you can extend x1. There is no rules. We keep it this one to have our maths simples. Okay, now let's draw these first segments. You have point A, which is 1425 newtons. You have this cut, capital M1 at a distance of x1. Right, so sum of the moment at cut equal to 0. Anti-clockwise is positive. M1 plus so M1 plus 1425 times x1 equal to 0. M1 equal to, let's put it in the bracket because we might need that one. Same thing, we can do the second cut. M2, which is 1500 newtons. UDL load of 2250 Newton per meters and at a distance of x2. So moment at the cut equal to 0. 1500 x2 minus 2250 x2 times x2 divided by 2 minus m2 equal to 0. M2 equal to 500 x2. Now 2250 1125. That is capital M2. Is exactly the same thing like we done it in the example number 2. You can see the trend is same, right? The different values, different loading condition, but x1, x2, finding the whole story, like finding M1, finding M2 is exactly the same. Okay. Now we're going to work through the virtual system. We redraw everything except the real loading. Point A has a pin, point B has a roller, 2.4 meters, and point C. Now the question is asking you to find the rotation at point C. So the difference here that we're going to put the virtual moment in the direction where the rotation would occur, right? So that is one. Now you might say, how do I know which way the rotation will gonna occur, right? As I mentioned, if you don't know, you might the loading should look like this by displacement curves look like, because you have this what we call, you have this loading condition. Based on these loading conditions in the systems, I would imagine this kind of a displacement curve in the dotted line. Do you agree with that? So if you have this kind of loading curves, then you might have a at this point here, and you might have these rotations going in these directions, you see, or you can have it rotations probably going this way, theta. So in that case, let's reverse it to this side, right? Again, this part, if you think that it's very hard for me to imagine, it's okay. You can put the one in the opposite direction, but then you will get the negative answers. Then you can comment why you get a negative answer, because your virtual load has the assumed direction is not correct. Okay, do you understand what I'm talking about? Yeah, so it's not scary part. There is, in this subject there is nothing scary part. I'm giving you all the logics and all the hints and all these the meaning for each answers. Okay, so if you think it's so hard for me to imagine the displacement curves that you done it, that's okay. You can put the, but you understand that point C you need to find the rotations, and you don't know the direction of the rotation, so you can put anyway. Okay, but let's put these in that directions. All right, now let's do the exactly the same thing in the virtual systems. Let's redraw the virtual systems again. So you know, let's say point A, point B, virtual systems here, 1 no unit, 2.4 meter, 1.2 meter. So let's find the reaction force AY and BY. Sum of the moment at A equal to 0, anti-clockwise is positive, -1 plus BY times 2.4 meter equal to 0. So BY equal to 1 over 2.4. You get 0.42, right? BY. And sum of the force in the y direction upward is positive. AY going up, BY going up equal to 0 plus 0.42. AY equal to minus 0.42, right? So if I redraw the virtual system again, 0.42, 0.42, 1, 2.4 meter, 1.2 meter, A, B, and C. Simple, right? So one virtual, you might ask why the moments, you know, we are finding rotation, so we put the moment virtual load. If you're finding displacements, we find the load. All right, and the points where we want to find the displacements. And point A and point B reaction forces, 0.42 going down and so on. So we're going to follow the same conventions, that cut number 1, x1, cut number 2, x2, right? We're not going to change it. We are not smart enough to do all these tricks. So we say that, okay, we will follow exactly the same in the real systems. Okay, so let's take the first one, 0.42a and small m1 at a distance of x1. So moment at cut equal to 0, anti-clockwise is positive, m1 plus 0.42 x1 equal to 0. m1 equal to minus 0.42 x1. Right, so your m1 positive, so positive, so that's good. Now we're going to follow the second cut. You have point C, you have 1, you have cut, you have x2, you have m2, right? The sum of the moment at cut equal to 0, so minus 1 minus m2 equal to 0, m2 equal to minus 1. Right? So far so good. Yeah, so now we're going to find the rotation at C. Let's say theta C, small m1 capital N1 E1 I1 dx1 plus small m2 capital M2 E2 I2 dx2, and this one 0 to 2.4 meters, 0 to 1.2 meters. You might say where this is coming from, because as you can see our initial that x1 is start from 0, finish it in 2.4 meters. x2 start from 0, finish it in 1.2 meters, right? So therefore we change those distances, right? And we keep it consistent, otherwise capital M1 and small m1 would not match. Now let's plug the values. EI is constant, 0.24 meters. Small m1, we found minus 0.42 x1. Capital M1, we found capital M1 minus 1425 x1, and dx1 plus 0 to 1.2 meter. Small m2 minus 1, capital M2 minus 1500 x2, minus 1500 x2 minus 1125 x2 square dx2. So 1 over EI, 0 to 2.4 meters, and 1425 times 0.42, you get positive 598.5 x1 square dx1, 0 to 1.2 meter, 1500 x2, positive 1125 x2 square dx2, and we just integrate 598.5 x1 cubed on 3, 0 to 2.4 meters plus 1500 x2 square on 2, 1125 x cubed on 3 on 3, 0 to 1.2 meters. So we just plug the value, 598.5 times 2.4 cubed on 3 plus 1500 times 1.2 square on 2. Sorry, this is just maths there. 3. And then if you solve this one, 598.5 times 2.4 cubed divided by 3. 2757.89 plus 1080 plus 648. So you got 4485.89 EI, right? So now we need the radian. Young modulus is given. Young modulus is equal to 9.8 gigapascals, and our unit is, you remember, Newton meter, right? Working in Newton meter. So let's convert that. 10 raised to 9 pascals. So 9.8 times 10 raised to 9 Newton per meter square. That is done. I. We have given the cross sections. If you can see in the diagram here, we have given the cross sections. Let me copy that. So we have given here these cross sections. So we can find BD cubed over 12. B is 75 millimeters times by 150 millimeter cubed. By the way, we can just convert this one into meter first instance. So 0.075 meter times by 0.15 meter cubed over 12. So 0.075 cube divided by 12, you get 2.11 times 10 raised to minus 5 meter to the power 4. Right, so we plug these values. 4485.89 over 9.8 times 10 raised to 9 Newton per meter square, Young modulus, and 2.11 times 10 raised to 5 meter to the power 4. (0.0217 radian positive), meaning our direction is, assumed direction is right. We get in these directions. Positive value, meaning that the virtual moment that we assume at the start in the virtual system is right, 1, right? We are recording it. If you have any questions there, you can ask me, or if you screwed up something or you want to stop me, some of